Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems, and today's module we will learn about deadlocks, how to detect deadlocks, and if deadlocks occur in a system, how to recover from deadlocks. So, the learning objectives are detection of deadlocks when you have a single instance of a resource as well as when you have multiple instances of resources, and recovery from deadlocks. So, first we will see about this deadlock detection. In an earlier class, in the earlier module, we saw how to avoid deadlocks. So, for avoiding deadlocks, the system needs to have a knowledge of what will happen in the system in the future, or the process should tell beforehand what will be the requests that will be made by each of them in future, and based on that the system will decide whether a request can be satisfied or not. And if you are not handling prevention of deadlocks or avoidance of deadlocks, and then what can happen is that deadlocks will happen in the system. And when deadlock is happening in the system, then you need to have some mechanism to find out if there are deadlocks in the system, and then when you find that there are deadlocks in the system, you need to have mechanisms to recover from the deadlocks. So, first deadlock detection when you have a single instance of each resource type. When you have a single instance of each resource type, you have a variant of this resource allocation graph again here, which is called a wait for graph. But here in this wait for graph, the nodes are only the processes. You do not have nodes corresponding to resources, and there is an edge from one process to another. Say there is an edge from process Pi to process Pj, if process Pi is waiting for process Pj, and in the corresponding resource allocation graph, how it would have looked is that from Pi to Pj, if there is an edge here, then there from Pi there would have been an edge to another resource Rq, and from Rq there would have been an edge to process Pj. And now this edge from Pi to Rq and Rq to Pj are collapsed, and you have just an edge from Pi to Pj, saying that this Pi is waiting for some resource that is held by process Pj. And after you have this wait for graph, you form this wait for graph, what you need to do is that you need to periodically invoke a cycle detection algorithm. So, you need to invoke an algorithm that will find out if there are cycles in this wait for graph. So, if there is cycles in the wait for graph, then it means that there is already a deadlock that has happened in the system. If there are no cycles, then there is no deadlock in the system. But this algorithm to detect a cycle in a graph, it requires an order of n square operations, where n is the number of vertices or number of processes in the system, number of vertices in the graph, or that corresponds to the number of processes that are involved in the system. So, look at this diagram. Here you can see that there is a resource allocation graph and the corresponding wait for graph is shown. Say for example, say P1 is waiting for resource R1 that is held by process P2, and now you have an edge directly from P1 to P2 here. So, P1 to P2 there is an edge. Very similarly for the other processes as well. So, this is the wait for graph. Now, to find out if there is any deadlock in the system, you just run a cycle detection algorithm in this graph. So, do you have a deadlock in this system? So, you find that say this P1 is waiting on P2 and P2 is waiting on P4, and P4 is waiting on P2. Very similarly, P2 is waiting on P3, P4, and but P2 is waiting on P4, etc. and so on. So, you find that you have a cycle in this, and hence there is a deadlock in the system. But this is the disadvantage here is that it is not suitable for resource allocation system when you have multiple instances of each resource type. So, when you have several instances of a resource type, then you can't use this wait for graph, but you can use a variant of the Banker's algorithm for detecting deadlocks. So, M is the number of resource types available in the system, N is the number of processes that are available in the system, and you have a vector called available. You have an array and length is M, you have M elements in the array, and each corresponds to the number of resource types. And if you look at this suppose if you have a vector like this, then it says that there are 2 instances of A available, 3 instances of B available and 0 instance of C available. And then you have another matrix called allocation, which is an n by m matrix. Rows correspond to the n number of processes and the columns correspond to the m number of resources. And you look at this example. So, here you see that A, B, C are the different resource types and P0, P1, P2, P3 are the different processes, and this allocation shows that how many instances of each resource is allocated to this process. And then you have another matrix, it is again an n by m matrix. This is a request matrix. So, this is different from the Banker's algorithm that you have. This is the matrix that indicates the current request of each process. So, here each process is currently requesting for some instances of resources that are available. So, if request of I comma j is equal to k for the ith process, for the jth resource type, this ith process is requesting for k number of instances. So, if you look at this, you see that you have A, B, C different resource types and P0 is currently requesting for 7 instances of A, 5 instances of B and 3 instances of C. And again you have notations here very similar to how you use in the Banker's algorithm. If you have 2 vectors x and y which are vectors of length n, then vector x is less than or equal to vector y if and only if each element in x is less than or equal to the corresponding element in y. So, the example, say you have x is equal to 1732, y equal to 0321 and each element in y is less than the corresponding element in x, and hence this vector y is less than or equal to x, and y is less than x if y is less than or equal to x as well as y is not equal to x, that is each element is less than or equal to the corresponding element in the other vector as well as it is not equal to the element in the other vector. And here you have rows in the matrices allocation and request, and each of the row is again treated as a vector. So, the row corresponding to allocation matrix is treated as, it is denoted as allocation I, and row in request matrix is denoted as request I. So, allocation I corresponds to the allocation, the resources allocated to process Pi. Request I corresponds to the resources that are requested by process Pi. And I will see how this detection algorithm works. You have 2 vectors work and finish of length m and n respectively, and you initialize work is equal to what is currently available, and for each of I equal to 1 to n, you check if allocation I is not equal to 0, and if allocation I is not equal to 0, then finish of I is equal to false, otherwise finish of I is equal to true. And then you go through an iteration where you try to find out if finish of I equal to false, and if request of I or the request of each of the process is less than or equal to what is currently available. If there is no such I, then you go to step 4. If there is some process whose request is less than or equal to what is available, you try to allocate that request for that particular process, and whatever will be allocated, whatever was allocated to that process earlier will also be released by that process, that will also be added to what is available. And you try and see if this can be done for all the processes in the system. If this can be done for all the processes in the system, then the system is not deadlocked. If you are not able to allocate for all the processes, if for some Pi, some process Pi you are not able to allocate, then this particular process Pi is involved in the deadlock. And this algorithm requires an order of m by n square operations to detect whether the system is in a deadlocked state. So, we will see an example of this deadlock detection algorithm. Here you have 5 processes P0 to P4, and you have 3 resource types A, B and C. There are 7 instances of A, 2 instances of B and 6 instances of C. And at time T0, the system looks something like this. You have 5 processes and whatever is allocated currently to each of the process is shown, and what is the current request by each of the process is also shown, and what is currently available is also shown. So, you have two instances of A that are allocated to P1, 3 instances of A allocated to P2 and 2 of A allocated to P3, and hence you have 7 instances of A, and the total all the 7 instances of A are currently allocated. Very similarly, 1 of B to P0 and 1 of B to P3 are allocated. So, the total 2 instances are allocated, and similarly 3 of C to P2 and 1 of C to P3 and 2 of C to P4, and hence the total 6 instances of C are allocated currently. So, no instance of any resource is currently available, but there are requests by few other processes. P1 is wanting some resources, P3 is wanting some resources, and P4 is also wanting some resources. P2 is not needing any resource, P0 is also not needing any resource. So, what we do, we now try to run the algorithm and try to find out if the request of this P1, P3 and P4 can be granted with what is currently available and the resources that are with the processes which are not waiting for any resource. So, here you see that P0 is not waiting for any resource, it does not have any request now, and P2 is also not waiting for any resource, it also does not have any pending request. So, we initialize the algorithm as work is equal to available, what is available? Nothing is available, 0 0 0, and finish of I is made false for all the processes. And we take the first process P0 and we check if the request of this process is less than or equal to what is available. Yes, and hence what we assume that this process is not wanting any resource. So, it will also release the resource that is currently allocated to it. So, it will become work will become 0 0 0, that is what is available currently, plus what is currently allocated to process P0. So, you have 0 1 0 as what would be available when P0 finishes off its work, and then this P0 is added to the save sequence, and then we look at the next process. We take the next process P1 and we check if the request of P1 is less than or equal to what is available. What is available now? It is only 0 1 0, and the request of this process P1 is not less than or equal to what is available. So, its request cannot be granted as of now. So, we now check with the next process. So, P0 is checked, P0 is fine, P1 is checked, P1's request cannot be satisfied. We check the next process P2. We check if the request of P2 is less than or equal to what is available. P2 has no request. So, whatever is allocated to P2 will also be added to what is currently available. So, work is equal to work plus allocation of P2. So, it becomes what is allocated to P2, that is 3 0 3. So, that is also added, and hence this becomes 3 1 3. So, what would be available in future is 3 1 3, and then we check the next process. We check process P3. So, what is the request of P3? It is 1 0 0. Can the request of P3 be satisfied with what is available? Yes, it can be satisfied. So, we have 3 A's, 1 B and 3 C's. P3 just needs 1 A, which can be satisfied with this, and hence what is currently allocated to P3 is also added to what is available. So, what work becomes 3 1 3 plus 2 1 1, you have 5 2 4, and finish of 3 is true. Now, we will move on to the next process. So, the next process is P4, can be allocated with what is available 5 2 4, yes, it can be allocated. Hence, what is currently allocated to P4 will also be added to this. So, it becomes 5 2 4 plus 0 0 2, it becomes 5 2 and 6. So, we are now able to satisfy the request of P0, P2, P3 and P4. P1 alone is pending, we check P1 next. So, when P1's request is checked with what is available, P1's request also can be satisfied now, and hence the system is not in a deadlock state currently. So, currently the system is not in a deadlock state. Find that there is a sequence P0, P2, P3, P4, P1. In the sequence, if you are trying to allocate resources, then the system will not be in a deadlocked state. And here you can see that there can even be more than one sequence. Here first time when I told you, you allocate for P0, then to P2 and then to P3 and then to P4, and finally you recheck P1 again. It is also possible to allocate for P0, P2, P3 and then check if P1's request can be allocated and then check for P4. So, it is also possible to have more than one sequence in this case. Now, with the current situation, currently there is no deadlock and the request of all the processes can be satisfied. But now if P2 makes an additional request for an instance of resource type C. So, the request vector changes like this. Earlier P2 was not wanting any instance of a resource, but now P2 wants one instance of resource type C. Now, let us see if the system will be in a deadlock state or not. P2 is requesting for one more instance of C, and what is available is 0 0, and the allocation is as it was in the earlier case. Now, we run through this algorithm. We just check if request is less than or equal to available for all of the processes. So, first process P0, request 0 is less than or equal to available, fine. So, whatever is allocated to P0 will be released. So, work becomes 0 0 0 plus 0 1 0, it becomes 0 1 0. Now, with 0 1 0, we try to find out if we can allocate the request of the other processes. So, first we check if request of 1 can be satisfied with this 2 0 2, but that is not less than or equal to what is available. So, we move on to the next process P2. We check if 0 0 1 can be satisfied from 0 1 0, that also cannot be satisfied. Because see, you need one more instance of C, here there is only one instance of B, no instance of A, no instance of C available. And then you try to check if you can satisfy the request of P3. P3 needs one instance of A, that cannot be satisfied. Then check if you can satisfy the request of P4. P4's request also cannot be satisfied. So, we see that the resources P1, P2 and P3 and P4, they are all waiting to get some resources, but the request cannot be satisfied with what is currently available. So, there is a deadlock in the system. Okay. So, even though you are able to claim the resources that are currently held by P0, P0 is not involved in a deadlock, and you can get back the resources that are allocated to P0, but even in that case you cannot allocate or satisfy the request of the other resources P1, P2, P3 and P4. So, there is a deadlock, and the processes that are involved in the deadlock are P1, P2, P3 and P4. So, with this algorithm we see that it is possible to detect deadlocks when you have multiple instances of a resource type. So, this is a variant of the Banker's algorithm. And if you look at the deadlock detection algorithm usage, we need to check when should we invoke the deadlock detection algorithm. Okay. So, that depends on how often is a deadlock likely to occur, and how many processes will be affected by the deadlock when the deadlock actually happens. So, if the deadlock happens very frequently, then you need to invoke the deadlock detection algorithm very frequently, and the resources that are allocated to the deadlock processes will be idle, because the processes are deadlocked, they are not doing any useful work, but they are also holding some resources which they are not using at all. So, the resources will be idle, and in due course of time the deadlock will grow. So, this process is deadlock, it is waiting for some resource that is held by other process, and in due course of time some other process will be wait for some resource that is held by the first process, and so on, and in due course of time the number of processes that are involved in the deadlock cycle will grow. So, deadlocks can occur when process makes a request and that request cannot be granted immediately. So, in this case what you can do is that you can invoke the deadlock detection algorithm every time there is a request for allocation, but that request is not able to be satisfied. You are not able to satisfy a request from a process, then you try and run this deadlock detection algorithm. So, this will identify not only the processes that are deadlocked, but it will also find out which particular process had caused the deadlock, because it is this process which is requesting, and after this process requested only you find that there is a cycle, because till the earlier request you would have run the deadlock detection algorithm and have found that there was no cycle, only then it would have come up to this level. And now this process requests for a resource and you run this algorithm and you find that there is a deadlock. So, you understand that this is the process that is actually causing the deadlock. So, the cycle is completed by the most recent request, and so that process that is requested recently is identified. But the problem here is that there is considerable overhead in the computation time. Why? Because each and every time there is a request, you need to run the algorithm, and the algorithm's complexity is high, and hence there is a lot of computational overhead. And the next method or next policy is to invoke the deadlock detection algorithm at less frequent intervals. That is, you can invoke them say maybe once per hour, or maybe you can invoke the algorithm when the CPU utilization is very less, maybe it falls below some 40% or 30% or so on, and then you can invoke this deadlock detection algorithm. And there can be many cycles in the graph. So, you may not be able to tell which process caused the deadlock in this case, because you are not invoking each and every time a request is made. You are only invoking only in frequent intervals of time, but there will be many processes in the cycle. So, you will not really know which is the exact process which caused the deadlock. So, now once you have detected deadlocks, you need to be able to recover from deadlocks. So, the simplest thing will be to inform the operator that a deadlock has occurred, and the operator can deal with the deadlock manually. Or what can be done is that you can let the system recover from the deadlock automatically, or what you can do is that you can break the deadlock. So, for breaking the deadlock, there are two ways in which you can do it. One is to abort or kill one or more processes, so that the circular wait will be broken. So, the process will be involved in the circular wait, one or more can be removed, and hence there will be no deadlock. The second way is to preempt some resources from one or more of the deadlock process. The deadlock processes are holding some resources and they are wanting for more resources, they are waiting for more resources. So, you can preempt the resources from the deadlock process and give to the processes which are needing them, so that the deadlock can be broken. So, first we look at the issues in process termination. For process termination, you need to abort all the deadlock processes. So, process termination, the first way in which you take about or go with this process termination is that killing all the processes that are deadlocked. So, if you have a system, if you run a cycle detection algorithm, you find that say some 5 or 6 processes are involved in the cycle detection algorithm, then you kill all these 5 or 6 processes. But this will break the deadlock, fine, but what will happen to the computations that all these 5-6 processes are done earlier? So, all these partial computations will be discarded and they will have to be recomputed later. So, the next way is, rather than aborting all the processes, what you can do is abort one process at a time and then try to run this detection algorithm and find out if there is still a deadlock. In this manner, you abort one process after the other and keep on running the deadlock detection algorithm again and again to find out if there is deadlock in the system. But the problem again here is that there will be considerable overhead, and after each process is aborted, you will have to run the deadlock detection algorithm again and again, and the time complexity of the deadlock detection algorithm is high, which means that you will be spending most of the time in this in computing or running the deadlock detection algorithm. And when you are aborting processes, in which order should you choose to abort the processes? So, you are trying to abort process one after the other. So, which one should be aborted first? That can depend on a number of factors. One is depending on the priority of the process. So, the process with the least priority can be aborted first. And then what you can do is, another way in which you choose a process is that you find out which process has computed so many computations, and if a process has computed a lot of computations, then that will not be aborted immediately. See, the process which has done only less amount of computations will be aborted. And another thing is that you also need to find out how much longer it needs to complete. Say it will complete quickly, then you do not abort that process. If it will take a long time to complete, then you can abort that process. And then next is based on the resources the process has used. If you had used a lot of resources, then why waste all those? Do not think of killing that particular process. And the number of resources the process needs to complete. If it needs many number of resources yet to complete, then you can think of aborting that process. If it needs only few number of resources to complete, then you can save that process. And then how many processes will need to be terminated? Okay, so if this process is terminated, then how many more will be terminated, and so on. And you also check if the process is an interactive process or a batch process, and so on. So depending on all these factors, or maybe some of these factors, or some of these factors, then you can decide on how you can choose a process to abort. And the next is resource preemption. So one way to recover from deadlocks is that to kill the processes involved in the deadlock. The next is to remove the resources from the waiting processes. Now again, when you are thinking of preempting resources from a process, you also have to decide on from which process you are going to preempt the resources. So you need to select a victim from whom the resources will be preempted. So how do you select a victim? You need to select a process such a way that the cost is minimized. And what is this cost? The cost factors can include the number of resources the deadlock process is holding, the amount of time a deadlock process has thus far consumed, has thus far executed, and based on this maybe you can decide, maybe you can even have other factors, and based on that you can decide on which process should be chosen for preemption. And now when you are choosing a process for preemption, what will happen to the state of that process? And what do you do with that process? Are you going to roll back that process to a previous state? Because you cannot continue, the process cannot continue, because you are removing some resource from it, and hence some resource will be missing from it. So it has to be moved back to some earlier state, some earlier execution state, which is a safe state, from where it can restart and it can continue. But the problem here is that it is difficult to find out a safe state, and hence we do not know really where to move this process back to. So what we do, you roll back the process, you do a total rollback, and that is very similar to aborting the process and restarting the process. And the next issue that needs to be addressed is starvation. When you are preempting resources from a process, there is quite a lot of possibility that the same process will always be picked as a victim. Maybe that is because of a low priority process or things like that. And you need to ensure that the starvation does not happen in the system. And hence for avoiding starvation, what can be done is that you can include the number of rollbacks as a cost factor. Okay. So, if a process had been rolled back say some 5 or 6 number of times, or maybe more number of times, then that process will not be chosen next time for rolling back. So, this count of how many times the process was rolled back earlier will be considered. So, now we have seen that for recovering from deadlocks, once deadlocks have occurred in the system, you need to recover from deadlocks, and recovering from deadlocks can be done using resource preemption as well as by aborting processes. So, summary of this module is we saw how you can detect deadlocks when there is a single instance for each resource type using the wait for graph. Then we also saw how you can detect deadlocks when there are multiple instances of the resources, which is a variant of the Banker's algorithm. We also saw that you can recover from deadlocks by aborting processes or preempting resources. References, acknowledgement. Thank you.